Hey, welcome guys. Yeah, so this is a new video series of the. I mean, I'm not serious. Yeah, so of the group representation. Yeah, so just my own record about my reading of the group representation and also my understanding. So I just took some course lecture. I took a course in when I was undergraduate, and I trying to make a note because I think group representation is interesting, and you can also advertise my YouTube channel. So you can go to a playlist, and there's mathematics, engineering, mathematics, calculus, probabilities, and yeah, some interesting lots. So there are a lot of videos that you guys can check. Hope you guys subscribe to my channel. Yeah. So today just introduction. Okay. So I think there are lots of video about the group representation, and but I guess some of them are very difficult. So I think these two are still okay and not very difficult to read. Or you can go online to find lots of lecture notes. Yeah. So I think I want to talk about the group representation of finite group, and for Lie group maybe in the future. So some keywords like a definition and a character and decomposition shows that the product user representation is an important keyword. So basically, I will talk about group representation of finite group, like an introduction or something. Okay, so yeah, so my basics that you guys should know what finite group is. Finite group is. If you don't know, you can go to my video list, and there's a group theory, or there's a group theory video list, and you can learn the basic finite group. Okay. Okay, so what is a group representation? Okay. Yeah, so let's give a definition. So the first definition is that right, you can given a group G, and so there's a operation, right? So let's say you map a G from G general linear group of V, where V is a finite dimensional vector space. So general linear group is the invertible matrix from V to B. So you can write T, this is V to B, right? So which T is invertible. Okay, and the V is finite dimensional, so you can view V as a complex vector space with dimension n, and this is just n by n matrices. And usually you can work any field like a finite field, rational field, algebraic field, whatever, right? And this map need to be a homomorphism. Okay. So where G, which means that phi GH. So now phi GH is a matrix need to satisfy phi G times phi H. Okay. So once you have this, we call that phi with V is a group representation. So basically, using linear algebra. So the key point is that using linear algebra to study finite group. Okay. Yeah, so basically, you can do that. One realize the general linear group. One you realize one use the matrix algebra to non-abelian property of matrix algebra to verify the property of the group. Yeah, let's maybe see some examples. Yeah, so this video first just talking about examples and finish this small video. Okay. So let's take a simple like a cyclic group of order 4, right? So you can write as a identity and a u square and u cube, right? And right, so we want to write as this operation. So right, so you can find in a 2x2 matrices, the identity should map to E, right? So E should map to identity, and this U can be written as maybe let's say U can be written as any operator. Let's say this is U, and you can compute U square and the U cube. And you can check that U to the 4 will become identity. Right, so obviously that once you fix this, then the rest are also fixed. So this is the group representation. So this is a group representation. So this map with this vector space 2 dimension is a group representation. Okay. Yeah. Okay. Yeah. So yeah, this is the definition. Okay. Let's maybe see some example. Okay. Okay. So let's let me see where we should use. Yeah, I mean we can talk about example. For example, if G is a Z6, whether you can generate by U use a 6 to identity, right? And you can not easy map from let's say row from G to right. So we can now I take it to the one-dimensional vector space by invertible, right? So it's the non-zero complex number, right? So any G, let's say U, right? I can map it exponential, let's say 2 pi I divided by 6, right? You can easily check that this is a group representation. I mean, maybe 2 pi divided by 6 is 1, and you can check that this is a group representation because U to a 6 will become, right, you map by notation. So row U will be this, right? And then you go to row to U6, we become exponential 2 pi I, right? Okay, so it's 1. Okay, and then you can check that if you pick K here, where K from 0, 1 to 2 to 5, right? You will get 6 group representation. So this gives you 6 group representation. And we will show that actually these 6 group representation are so-called irreducible group representation. So there are 6 of them, right? And then you can in the future we can prove that these are all the irreducible representation of this one. Okay. Okay. Yeah. And also, let me just write down. So if you get the group representation, okay, so this is a general linear group of n by n, and this n is called dimension. Okay, and if n is if row is injection, so injection means 1 1 means that if x and y are different, they should be mapped different. This is called a fail-for representation. Okay, so any group always has a group representation, right? I mean, if you map all the G to 1, right? You take the trivial vectors, the dimension 1 vector space and map any G to 1, it becomes a non-fail-for group representation. So it's not clearly from here that any group will have a fail-for representation. It's not clearly. Okay. Yeah. Okay. So let's say it's not directly see that anyone will give you the fail-for representation. Okay. And also just what I say, right? So for any n, for any pick out any integer, right? So you can define any group element G to the identity n by n matrices. So this is not fail-for, right? Because any matrix map to identity, and then you can easily check that where this is satisfied because identity times identity is identity. Okay. Okay. Also definition. I want to say that whether two representation are equivalent. Okay. So suppose you get two representation. One is row 1 G from general linear group and C, and then you get another row 2. So the equivalence should only be defined when their dimension is the same, right? Is equivalent. If there's a P, which is a matrix general linear group from and C, such you can view this P as just change your basis. So such that the row 2 is the same as P inverse rho 1P, right? So this is a changeable basis. So this means that the rho to G for any G belongs to G is the same as P inverse rho 1G P. Yeah, so this is just a changeable basis, right? So in the linear algebra, changeable basis formula looks like this. Change of the basis. Okay, so somehow like we didn't see something very useful. Just give a definition. Yeah. So yeah. So this is the introduction. Yeah. So let's define. Let's just before we finish, let's define a very simple idea called a constructing representation. So this is the first group representation for any group that you can always construct, and usually it's not irreducible and very large. Okay. So we know that any subgroup by the KD theorem, any subgroup, any G is a subgroup of symmetric group, right? So it should be this, right? So let's suppose that so there are constructions that suppose suppose G is a subgroup of Sn for some n, and we want to construct a group representation in this case. Okay, so let's say V is a vector space, right? Such that we pick up basis. So let's say we pick up basis span of, let's say B1, B2 up to maybe Bn. And we know that any group G, so any element G is just a permutation, right? Because I already restrict G is a subgroup of Sn, so G is a permutation of these n ladders, right? With this ladder, right? So, or you can say that G permutes this B1 up to B2, right? So now you can easily define a map from G, rho G from V to V, right? So remember that rho G is a linear transformation, right? So it should be V to V, or you can write automorphism of V if you're crazy, okay? Such that your rho G econ BK, so BK is a label, right? Map to define to be what? Map to B G of K, right? So G will permute K, right? So just permute. So you can view that this matrix is something very some of these 0 and a 1 1 or something. So just a permutation matrix. Okay, and also rho GH, right? Will map to BK into BGHK, right? But the BGH are already group element, right? So yeah, so right, you HK and the GH and you permute, right? So by definition, this is just a rho GH. Okay, so it's a group representation. Okay, so let's see an example. Maybe see example is not make you easier to understand. So let's say G is an identity, and then 1, 2, 3, 3, 2, 3, 1, 3, 2, right? So this is I think this is what? This is a cyclic group with order 3, right? Yeah, I think it's order 3 and a subgroup S3, right? So this is actually G is isomorphic, I guess these 3, right? So yeah, so we can take a V to be the standard basis, right? Because we have a 3 of them. And let's take 1, right? So 1 is identity. So 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, right? How about 1, 2, 3? So 1, 2, 3 map 1 to 1, right? What shift 1 to 2 to the 3, 3 to 1. Right? So this should be this. Right. So this make 1 to 2, 2 to 3, 3 to 1. Also, you can check 3, 1, 3, 2, push map 0, 1, 0, 0, 0, 1, 1, 0, 0, 0. Right, like this, right? Right, so yeah, you can check this. Okay, so from here, yeah, so by the KZ theorem, right, we know that we can always use this to construct any group representation, right? So for any group, there's always exists at least one group representation, which is maybe yeah, but not trivial. Okay. Yeah. So there's a definition that let me just write down, right? So from here, so from KD theorem, so any group with order n, right? So the order n has a group representation, has a subgroup, is a subgroup of Sn, right? So if we use these to construct this group, if we use these to construct a group representation, this is called a regular group representation or regular representation. Okay, so today we give some definition and we talk about how to use the KD theorem, which if you can embed your group in your subgroup or symmetric group, then you can at least construct one representation. And I think by definition, this guy should be faithful, right? Because we permute something, right? So there's no two group act exactly the same because you're already embedding it into the symmetric group. Okay, and yeah, next video we talk about subgroup and what's a subgroup representation, and also we talk about the short lemma. I think finite group representation is not difficult, so hopefully this video list will not take so long. Okay, see you guys next video.